Assalamualaikum warahmatullahi ta'ala wabarakatuh, and a good day to all. Alright, so for today I would like to continue our lesson, which is still in electrostatic field in a medium. However, for today we will discuss more on dielectric. Okay, so before we have looked into conductor medium, and today we will focus on dielectric medium. All right. Okay, now, so the first of all, we will go under dielectric under static conditions. Okay, we will look how the behavior of dielectric under static conditions. All right. So first of all, okay, as I mentioned in this chapter, we will deal with three things, where the first thing is the medium. Okay, now let's say that we have a medium here, and this medium, since that this is under a topic of dielectric, we assume that the medium is a dielectric medium. Okay, and the another component that we should have is electric field. Okay, so the applied field. So now the applied field is denoted as this direction, okay, towards upward direction. And the third component that we need, or that is required, is the charges. Okay, when now it is denoted that the charge is a volume charge, okay, as rho v. Okay, now let's recall the continuity current equation that we have learned before. If you still remember, there are three model of current equation, and one of them is continuity current equations. So let's recall the continuity current equation. Okay, so in continuity current equation, it is denote that rho v is equals to rho v naught rho v naught to the power e of minus the sigma over epsilon naught time. Okay, so now let's try to plot a graph of rho v in terms of time. Okay, what will happen to this? You want to see what will happen to these charged particles, okay, in respect to time. Okay, so now we have two axes here. One is rho v, okay, as y-axis, and time as x-axis. Okay, so first of all, let's look when t, or the time, is equals to 0. What will happen to our rho v? So when time is equals to 0, this component, okay, this component will be 0, and therefore our rho v will be equal to our rho v naught. Okay, so when time is equal to 0, okay, so it means that there is no electric field applied on this particular in this specific time. So it means that our rho v will remain, or will equal as rho v naught, which is our essential rho v. Okay, so what will happen when the time is increasing? Okay, where the time is no longer equals to 0, and on that time, okay, our electric field also will not be as a 0. Okay, so remember, when the time is equals to 0, our electric field by right is also equals to 0. It means that there's no field applied to this medium. However, when time is increasing, it means that there is a field applied in the medium, so the field is no longer equals to 0. So when time is larger than 0, okay, the electric field is no longer equals to 0. So what will happen to this charges particle? It will remains. If you look in this graph here, it will remains. Yeah, rho v will remain same when exposed. The rho v will remain same when exposed in electrostatic field. Okay, so here we can summarize that for dielectric, under static conditions, the sigma here, the sigma will be very small, okay, will be very near to zero, and it is assumed to be very small. Okay, did you still remember what the sigma is? The sigma is conductivity actually, yeah. So it means that our dielectric medium, yeah, our dielectric medium by right is not a good conductor, right? So we assume that this sigma is very small, the value is very small, and we assume that it is near to zero because it is not a good conductor. Okay, it is a very bad conductor, so we assume that the conductivity value, which is the sigma, will be very small, where it is the value is very near to zero. And it means that for a dielectric medium, okay, a very good dielectric medium, okay, very good dielectric medium, okay, the value of permittivity, the value of sigma, or the conductivity should be very near to zero. So that is what we can say, yeah. So here is the conditions or the behavior of dielectric under static conditions. All right, now let's look on the microscopic view, which is an atom. Okay, we assume that the medium is it is look like an atom, okay, which is a very very small structure. Okay, so when we deal about an atom, I think most of you know about this Bohr diagram. Bohr atom diagram. I think this is very famous. I think most of you should know this. So the Bohr atom diagram is look like this, where in the middle there's a nucleus. Inside the nucleus there is a proton. All right, and there is an orbit. Okay, there is an orbit outside of this nucleus, and that orbit, yeah, or shell here is filled with electron, right? And this electron is moving. Okay, so this condition is happen. Why it is not moving? Oh, sorry. Okay, so this condition is happen when this condition, so we assume that this condition, the original Bohr atom diagram, okay, is in condition where there is no field applied, electrostatic field applied to this structure. So it is look like this, all right, where the electron is orbiting the nucleus, okay, and the nucleus is contained with positive charges, all right. Okay, what will happen to this Bohr atoms diagram when this electric field, when there is a field applied, when this electric field is no longer equal to zero? It means that there is electric field applied. So when there is an electric field applied, the Bohr atoms diagram will look like this. Since that the electric field is applied in this direction, all the electrons, yeah, all the electrons will be positioned, okay, will be arranged, yeah, in the location where this electric field is penetrating this atom diagram. Okay, if the electric field applied is in this direction, can you guess where is this electron will be? Where will be the position of these electrons? Good. So the electron position will be in this way. Okay. So the electron position will always follow where or the direction of this electric field when it is penetrating a medium. Okay. So it means that in this case, the electric field is penetrating this atom diagram at this direction, okay, at downward direction. So it means that the position of this electron will be arranged at the upward here. Okay, if the electric field applied is upward direction, so the electron arrangement will be at the bottom of this diagram. Okay. Okay. So now let's look, okay, how we can simplify this diagram. Okay, so this diagram we can arrange. Okay, so I think I should erase this here so that you will not be confused. All right. So this diagram, all right. So this diagram can be arranged to this diagram, right? So I make it simplified. So since that the negative charges is arranged at the bottom part, so by right the positive charges should be the opposite direction, right? Which is at the upward here, all right? And this D is denote to this electric field. Okay, so from this diagram we can simplify it to be like this. Okay, and from here, okay, and from here, okay, we can say that both of these two charges to be as a dipole. Okay, and that's why it is denoted as D here. Okay, where this D is the dipole of these two charges in the direction where the direction of electric field is this way, is in this direction, and therefore we can rewrite this structure to be as this equation. Okay, where P, okay, where P, which is small letter here, P small letter, which is there is a vector where the direction is depending where the electric field is applied, is equals to Q, okay, is equals to the charges and the dipole of the charges. Okay, so this charges has a dipole, and this dipole also have a direction where the direction is depend on where the electric field is applied. Okay, so this P is actually called as electric dipole moment. Okay, electric dipole moment. So since that this is a microscopic view, means that it is an atom, we assume that this is an atom, so that's why this P is written in small letter. So now let's go to microscopic view, where we assume that there's groups of atoms. Okay, so let's say that we have a medium here. Okay, so this medium is unpolarized dielectric material. Okay, there is no polarization in here, so that's why it is unpolarized dielectric material. So it means that when it is unpolarized, what does that mean? It means that there is no electric field applied, so the electric field applied is equal to 0, and therefore the polarizations also will equals to 0. Okay, the P is also equals to 0. Why the P is equals to 0? Because there is no electric field is applied to this structure. Okay, so nothing gonna happen to this part. Yeah, so now let's assume that we have the same medium, we have the same material, but now the material is polarized dielectric material. Okay, it is a polarized dielectric material, and therefore there is electric field applied, okay, to this structure. So when there is electric field applied to this structure, it means that there is a dipole exists, right? Okay, it means that there's a dipole moment exists. So I just denote it as this direction, okay, where the direction is like this. So it means that the minus, which is the electron is downward here, and the positive, which is the proton, is upward here. Okay, so now let's say that the dipole moment have 4. So I make it as there's a 4 dipole moment, and I make it like this. Yeah, let n, which is the dipole, n is referring to the dipole. Yeah, let n is equals to 4, so it means that there is a 4 dipole moment here, and therefore, since that there's electric field is applied, okay, and this is a polarized dielectric material, so it means that the P is no longer equals to 0. However, the P can be rewrite as, okay, P where it is a vector is equals to the limit, okay, which is when V is larger than 0, okay, means that there is a the volume, okay, of the medium is larger than 0, so it means that there is a dipole inside here, and the dipole is summarization. Okay, this is a sum. This is a dipole when 1, okay, to how many dipole it have. So since that in this particular medium there is a 4 dipole, so it means that there is a 4 here, okay, and summarization of the small dipole here, yeah, pi, so over the divergence of V, okay, the divergence of V. So you can see here that when the electric field is no longer equals to 0, it's not 0, the polarization also is not equals to 0, okay, and it has the same direction as field applied, okay, as field applied here. Right, so from here we can say that the polarization of dielectric is equals to, okay, electric susceptibility. Okay, this symbol means that electric susceptibility times with electric times with sigma naught, sorry, not, it is not sigma, it is epsilon naught, and times with the electric field. Okay, so here electric from here, yeah, electric susceptibility here, it means that how the dielectric material respond to this electric field. Okay, so the value of electric susceptibility here shows to us how the material, which is the dielectric material, responds to electric field. If the value is larger, it means that the dielectric medium, okay, that particular medium is responsive, yeah, is responsive to electric field. If the value of this electric susceptibility is lower, it means that the value, the medium, okay, the structure, the medium is non-responsive, okay, it's not response to electric field. Okay, so from here also we can define what type of the material it is. Okay, either that particular medium is a conductor or dielectric. Okay, so the value of electric susceptibility for conductor will be higher, for dielectric will be lower. Okay, so from here, okay, we can see that, okay, from electric applied, okay, when there's a dielectric exposed to electric field, okay, we can say that when dielectric is exposed to electric field, it will produce the polarization. Okay, it will produce P, which is denoted as polarization. Okay, so now we want to observe, or we want to see how this P, okay, how this P produce new charges. Can this P produce new charges? All right. So charges due to P, okay, how the charges will react, or the behavior of the charges when there is a polarization inside that particular medium. Okay, so now let's say that we have a medium here. Okay, so of course this medium is dielectric, because we are discussing about dielectric now. So this medium is dielectric medium. Okay, and since that there is an electric field applied to this medium, okay, and before that, let's say that this is the z-axis, this is the x-axis, and this is the y-axis. Okay, and since that there is electric field applied to this medium, so it means that, of course, there is a dipole inside this particular medium, right? So this is positive and negative, okay, positive and negative dipole. So the negative will be positioned as posited at the bottom because the electric field is applied at this direction, right? If the electric field applied is opposite way, so this dipole also will be in opposite way. All right, so let's assume that all this structure, okay, is is filled with all the dipole, okay, with all dipole. So we from here we can see at the at the surface of this upward medium, it is full with positive charges. Okay, it's full with positive charges, and I denote it as rho SB. Okay, rho SB. All right, rho SB, it means that surface charges. Okay, and B here, it means that it is bounded. Okay, it is bounded charge density. It is bounded together. Okay, the positive charge, this positive charge is bounded to electron, so it is not freely moved. Yeah, it is not freely moved. These charges is not freely moved because it is bounded to this electron. Okay, so that's why instead of rho s, it is rho sb, because it is bounded surface charge. And what will how about this the bottom layer here? So the bottom layer here is negative charges, so we can denote it as minus rho SB because it is also bounded to this positive charge. So it means that it is not freely moved. Yeah, so however, please bear in mind that this rho SB, okay, this surface bounded charge is only present or only exists when there is a polarization vector here. It means that when there's electric field applied here, okay, there will be no bounded surface bounded charge if there is no polarization and there is no electric field applied. Okay, so now we can say that at the above layer here is positive charges, and the lower layer here is negative surface filled with negative charges. Yeah, so since that the direction of E is upward here, okay, so here this is a bounded surface charge density. So since that our electric field is the direction is upward here, so the direction of vector also will be upward here. Okay, therefore we can say that the rho surface bounded, okay, rho surface bounded charge is equals to polarization dot product with the direction of with the direction with the particular directions lah, which is depending on where electric field is applied. All right, okay, so now let's look here. Since that the E is on a z direction, so our E will be EZ at z direction, right? And how will be the P? P, where the polarization also will be PZ at z direction. Am I right? Okay, now let's discuss this particular structure into surfaces. Yeah, and let's say that the above here is surface number 1, and here will be surface number 2. Okay, surface number 2 will be downward here at the bottom here. Yeah, here will be surface number 2, and here, yeah, will be here will be surface number 3. So let's discuss this. Okay, into three different surfaces. Yeah. So let's say that rho S be at surface number 1 here. Okay, rho SB1. So how will be the value? Okay, so it will be PZ, since that the equation is like this, yeah? Since that the equation is this, so PZ, okay, in Z direction. In the Z direction, dot product, okay, because this is in a vector form, yeah, so please don't forget about this, the direction of the polarization. Since that surface number 1, it is directed on Z direction, okay, positive Z direction, so it will be Z direction. And how about the vector? So the vector also will be Z direction, okay, this is a dot product. So from here, Z and Z is same direction, so we can say that this will give us 1. So this value, yeah, so the rho SB at surface number 1 here is in a positive value. Am I right? Okay, it will give us positive value. Why? Because it is same direction as Z direction. How about rho SB2, where it is located at the bottom here? So I think by you already have the picture where it will be rho as Z, which is same Z direction, okay, because our polarization is depending on electric field, so our electric field is same direction with Z, so it will be Z direction. However, now this surface is located at the bottom and the direction is downward, so it is opposite direction with this Z, so it will be minus Z direction. And this time with this, okay, the dot product of same vector direction, since that it is 1, however, since that this is minus, so you can see that the value here, it will give us minus value or negative value. So what does that mean? It means that the direction of this, yeah, is different direction. Okay, all right, so how about surface number 3, which is at this particular part? Okay, rho SB3, so it will still, our polarization value still in the Z direction, and surface number 3, the direction is in Y direction, right? So it will be Y direction. So you can, you already know, when there is a different direction, when dot product of different direction, it will give us 0. So the value of rho SB3 here will be automatically 0. Okay, so you can see here, I think by right you already have the picture where the where if the direction of the surface is different with the polarization, it will give us 0. For example, these surfaces will give us 0, and this surface also will give us 0, because this surface is in X direction, right? So it also will give us 0. So the only value, the only surface that will give us value is this particular surface, which is the upward surface, and the bottom surface here. All right. Okay, so okay, so now I think we have discussed about the surface. Okay, the surface charge density for this particular medium when there is a polarization. Okay, so now let's discuss about how about the volume of this particular medium. Okay, so the volume of this particular medium, okay, will be bounded volume charge density, and the formula will be rho VB is equals to minus divergence dot product of P. Okay, minus divergence dot product of polarization. Okay, so the volume also will be rewrite as subscript B, because it is a bounded charge density. So it means that, what does that mean again? It means that all of these charges is not freely moved, all of them is bounded together. Okay, Okay, so from here we already discussed about how the electric field applied will produce the polarization, and how the polarization affect the charges. Okay, where the polarization here, yeah, will give us rho SB, surface bounded, and also will give us volume bounded. Okay, now let's look the feedback effect. Okay, the feedback effect. Okay, so what is feedback effect? Okay, we want to observe. Yeah, feedback effect is we want to observe what happened to this E applied when charge is introduced. Okay, and how does the charge influence? Okay, how does this charge, how does this particular charge influence the E applied? We want to see how this particular charge influence to E applied. Okay, influence the E applied who produce the charges. Okay, so that's what we call the feedback effect. We want to see how this particular charge uh, influence this E applied, where actually this E applied is producing this charge, right? So you want to see what is the feedback effect. So let's recall the Maxwell equation that we have discussed before. So in free space, yeah, we know that this particular equation in free space, where the divergence of D, electric field density, is equals to rho V, and since that this D is equals to the epsilon naught E, so we can rewrite it as divergence of epsilon naught E is equals to rho V. However, these cases is only happens in free space. So what will be the difference in dielectric? Okay, so in dielectric, okay, by right, yeah, it's just same. Okay, it's just same, where it is divergence of electric divergence of epsilon naught electric field intensity. Okay, there should be additional here, okay, which is equals to, we know that dielectric, the charges is rho V plus rho VB, right? Rho V plus rho VB, if in a dielectric, right? From what we have discussed before, the dielectric will produce to us rho VB, right? So let's say that if we have a dielectric, okay, and free space, okay, dielectric plus free space. So this is dielectric, this is dielectric, this is free space, this is free space. So by right here also should be some additional, right? So how we want to define what is additional here? So we have learned before that from the D, yeah, from the D, which is electric field density, is equals to epsilon naught times with electric field intensity. So this is in free space. However, in dielectric, there's additional, which is polarization is introduced. Polarization is introduced. So by right, the electric field density, if there is a free space and dielectric, so the value of free space just plus with polarization. Okay, because in dielectric there is a polarization introduced, so we can rewrite this equation to be P is equals to D minus epsilon naught E, right? So from here, okay, from here we can know that, from here we have discussed earlier that P is equals to electric susceptibility times with epsilon naught electric field intensity, right? So by right, we can insert this equation inside this, and we can rewrite the equation again to be the D, the electric field density, for medium of, remember, yeah, this medium is dielectric plus free space. Okay, so it can be rewrite as epsilon naught 1. This is for free space structure, and for dielectric will be plus, not only dielectric, for dielectric, yeah, plus electric susceptibility epsilon naught E. Okay, and from here, this particular part actually, 1 plus electric susceptibility here, we can rewrite it to be as epsilon R. So what is epsilon R? So epsilon R is actually dielectric constant. Okay, it is actually dielectric constant, and also known as relative permittivity. Okay, relative permittivity. So from here, yeah, from this electric susceptibility, you can introduce another epsilon value, which is at relative permittivity, which will be epsilon R. Okay, right. And from here, okay, if we go back to this equation, okay, rho VB, if we look at this from previous slide, which is from here, rho VB, we can rewrite is minus divergence dot product with polarization here. So that's mean, okay, so that means that this particular can be minus divergence B, okay, plus rho V equals to epsilon E plus P. Okay, so this will be, so the one that we don't know here, it is actually can be rewrite like this. All right, so from here we can see that from what the feedback, yeah, from the feedback effect, actually we can derive, or we can know the value of relative permittivity. Okay, where it is actually a dielectric constant. Okay, so this summary, yeah, this summary show us, yeah, how dielectric material responds to electric field. Okay, this, yeah, show to us how dielectric material responds to electric field. The higher the value of relative permittivity, okay, the higher the response to electric field applied. Okay, the higher the value of electric permittivity, the higher the response to electric field applied, right? So each particular medium have different value of relative permittivity, right? So now let's discuss when there is a boundary conditions. Okay, so boundary conditions, we have discussed this in conductor before, okay, where a conductor and a free space, if you still remember. However, in this particular topic, we will discuss dielectric. So it means that those two medium is dielectric boundary conditions. So let's say that we have two material here, okay, those materials, if is dielectric material, however the value of electric material, electric relative permittivity is different. Okay, one is denoted as epsilon 1, okay, and another one is denoted as epsilon 2. Okay, so although it is dielectric material, but the types is different. Okay, so same as what we have discussed in conductor boundary conditions. So the surface of this, the surface, yeah, is filled with positive charges. Okay, the surface is filled with positive charges. All right. So let's say that we have a boundary here. Okay, this is where the boundary here, and we have E2, where the directions of the propagations of wave from E2 will be start changing after passing through these boundary conditions, and this is denoted as E1 and this is denoted as E2. and as what we have learned in conductor, it is same when it is actually can be separate. E1 can be separated into E1 normal and E1 tangential, where normal is 90 degrees to the boundary. Normal is 90 degrees to boundary, and tangential is actually 0 degree to the boundary. Okay, so each of them, for E1 and E2, all of them can be separated into two different components. Okay, one is the normal component, and the second one is tangential component. All right, so let's discuss this based on each component, which is the normal component and tangential component respectively. So for the normal component, okay, boundary condition 1, which is referring to the normal component, same as what conductor, d1n minus d2n is equals to rho s. Okay, this is equation number 1. Okay, and for boundary condition number 2, which is on the tangential component, electric intensity at the tangential is always equals to electric intensity at the tangential in the second medium. Okay, so this equation is same for dielectric and same for conductor as well. All right, so think from here. Okay, let's try. Okay, I would like you to try first these equations by yourself. Later on I will give to you the solution. Okay, let's try two extensive homogeneous isotropic dielectric meet on plane z equals to 0. Okay, they meet. There's two components of dielectric. Okay, both of them is dielectric. This is component number 1, this is component number 2, and they meet on plane z equals to 0. Okay, for z larger than 0, which is at this component, ER1 is equals to 4, and for z lesser than 0, okay, the ER2, which is the value of relative permittivity, is equals to 3. Okay, so you can see that both of these, each component is made from different materials. Okay, however, both of them is dielectric, but the types is different. So a uniform electric field E1 is equals to 5x direction minus 2y direction plus 3z direction kilovolt per meter exists for z is equal, larger or equals to 0. What you have to find, you need to find E2 when z is lesser or equals to 0, and the angles of E1 and E2 make with the interface. All right, so I would like you to try to solve this, try to figure it out first by yourself, and I will give the solution. I will let you know the solution later on in next video. So hope you will try this to solve this by yourself. Okay, and see you on the next video, inshallah. So thank you very much. Okay, I know now is a mid-sem holiday, so I hope you will still not forget about your EMT course. All right, and see you in next video. Okay, thank you very much, and have a good day, everyone.